All right, diving in today. Get ready, because we're going deep on something pretty wild using quantum teleportation to, well, supercharge web crawling. Yeah, think about the internet for a second. It's this massive, crazy, ever-changing thing, right? Like a gigantic, constantly shifting ocean of data and, just keeping up with it all. That's a huge challenge for the web crawlers we use today. So we're going to explore how these honestly kind of bizarre principles from quantum mechanics could actually give us a totally new advantage.
Yeah, exactly. And we've got some really interesting research here looking at how quantum teleportation, along with other quantum computing tools, could totally revolutionize the tech behind web crawling.
Okay, so before we go too far, let's make sure everyone's on the same page. Web crawlers, sometimes called spiders or bots, they're basically the things that constantly browse the web for us, right?
Yeah.
Following links and gathering all that info.
Right.
So traditionally, they work with what's called a URL frontier. Think of it like their to-do list, a list of web addresses to check out. And then they have a fetcher that actually grabs the pages, a parser that pulls out the useful stuff, and a content processor that analyzes it all. Seems pretty straightforward, but the scale of the internet, it's insane.
Absolutely insane. And as you said, that scale is exactly what causes so many problems for this traditional approach.
Yeah.
Because the internet is just so huge and it's changing all the time,
Right.
that just puts a massive strain on resources like processing power and storage. And then you've got the whole deep web thing, all that content that's hidden from those standard links and, the incredible variety of content formats out there.
Yeah.
And then on top of all of that, there's the whole challenge of actually understanding, like the actual meaning embedded in all that data. It's a lot.
Yeah, it's like, I don't know, trying to organize this infinite, constantly reorganizing library with a team that's way too small for the job, right? So, okay. Quantum teleportation, how does that even fit into this picture? So basically, it's this mind-blowing process, right? It's where you transfer the quantum state of a particle to another particle. But get this, at a distance, without any physical movement between them.
Right.
It's like, what? Instant transmission, but for quantum information.
Yeah, and the really mind-bending part here is this whole concept of quantum entanglement. So imagine, right, two particles, but they're linked in this super fundamental way, so deeply connected that no matter how far apart they are, they share the same fate. It's like if you measure a property of one particle, boom, you instantly know the corresponding property of the other one. And that interconnectedness, that's the key to all of this.
So this is where things get really interesting. In quantum teleportation, you have a sender, right? We'll call her Alice. And a receiver, we'll call him Bob. First, they need to establish a quantum channel between them. They do this by sharing an entangled pair of qubits. Right.
And just a quick reminder, a qubit, it's not just a 0 or a 1 like a normal computer bit. It can actually be both at the same time. It's called superposition. And this opens up all these totally different possibilities for computation, like parallel searching through all that web data, which is potentially incredibly powerful.
Yeah.
So Alice, she takes the qubit with the state she wants to teleport, and she does a joint measurement on it and her part of the entangled pair.
Yeah.
And then after that, Alice has to send the results of her measurement over to Bob. But she does this using normal, classical communication, like sending a text message or something.
Okay.
And then, based on that information, Bob, he applies specific quantum operations to his part of the entangled pair. Get this.
What happens?
Bob's qubit now has the exact same quantum state as the original qubit that Alice wanted to teleport.
Whoa.
It's as if the information just, jumped across space. And, that entanglement we were talking about, that's the crucial ingredient here. So it creates that quantum channel that makes this whole transfer possible.
Okay, so I'm starting to get it now. And researchers, they've actually shown that you can do this over pretty significant distances.
Oh, yeah. I mean, they've done it using optical fibers. They've beamed signals through free space, even using satellites.
Wow.
Yeah, it's pretty wild. And it shows that this isn't just some theoretical idea. It actually has real potential for long-range quantum communication.
So it's like, okay, we can actually do this. But I'm guessing it's not as simple as, I don't know, just flipping a switch, right?
Yeah, there are definitely some pretty big hurdles to overcome before this becomes commonplace.
Like what?
Well, one of the biggest challenges is that quantum states are incredibly fragile. They're easily disrupted by, well, pretty much any interaction with their environment. They call decoherence.
Decoherent?
Yeah. Think of it like a perfectly balanced spinning top.
Yeah.
Any tiny little wobble or disturbance, and it's going to fall over. And it's kind of the same with qubits. Even the slightest bit of noise from the environment can disrupt their delicate quantum state. and that can cause the information they're holding to be lost.
And in those real-world experiments, the accuracy of the transfer, the fidelity, it's not always perfect, right?
Yeah, that's right. And then there's the whole challenge of just creating and maintaining those entangled qubits in the first place. That takes a lot of resources. And, we can't forget that right now, quantum computers have a pretty limited number of these qubits, which really restricts how complex we can get with quantum teleportation. Scalability is definitely a major bottleneck right now.
So lots of challenges, but it sounds like people are working on this stuff pretty actively, right?
Oh, yeah, definitely. It's a really hot area of research. Scientists and engineers are constantly coming up with new techniques to improve the stability of qubits, make the teleportation process more accurate, reduce those resource demands, and, build bigger and more robust quantum systems. So, yeah, we definitely have limitations now, but things are moving towards greater practicality.
Okay, so we've talked about the huge challenge of web crawling today, and we've laid out the basics of this honestly kind of crazy concept of quantum teleportation. So now let's put it all together. How could this quantum capability, along with other quantum computing tools, really change how we crawl the web and understand all that information out there?
Well, the research here really points to some potentially dramatic improvements in efficiency, how fast we can do things and how we use our resources.
Okay.
And the vision isn't really about completely replacing all our classical crawlers. It's more about a smart hybrid approach, right? Intelligently using the unique strengths of both classical and quantum computing.
So a best of both worlds kind of thing. So one of the quantum tools that keeps coming up is something called Grover's algorithm.
Right.
And, for anyone who's not super familiar with quantum computing, what makes this algorithm so relevant to the whole web crawling problem?
Well, think back to that massive list of web addresses a crawler has to deal with, that URL frontier.
Mhm.
Grover's algorithm, what it does is, it can actually search through unstructured data way faster, like quadratically faster.
Quadratically faster. Okay, can you break that down for me?
So imagine you're searching through, I don't know, millions of URLs, trying to find the most promising ones, right? A classical algorithm, it would take a certain amount of time. But Grover's algorithm, in theory, it could do the same thing much faster.
Okay.
And that speed up is proportional to the square root of the time a classical algorithm would need.
Okay, that's a huge potential efficiency boost, right? Especially when you're talking about prioritizing which parts of the web to explore.
Yeah,
And
exactly.
it's not just about that initial list of URLs, is it?
No, not at all.
Because the research also suggests that Grovers could be really helpful in quickly finding specific content within all that data that's already been crawled, and even in, spotting duplicate content much faster.
Right, exactly. And then, building on the power of Grover's, there's this even more general technique called quantum amplitude amplification.
Quantum amplitude amplification. Okay.
Yeah, think of it as a way to boost the chances of finding the solution you're looking for in a huge search space.
Yeah.
So in the context of web crawling, this could be really valuable for refining how we decide which URLs are the most important to look at.
Okay, so making sure we're focusing on the most relevant stuff.
Exactly. And making the best use of our resources, across the whole distributed system.
Another really exciting possibility that's mentioned in the research is something called quantum machine learning, or QML. And that sounds like it could make web crawlers a whole lot smarter.
Yeah, exactly. So, we've been talking about how to make web crawlers more efficient, but QML could actually lead to breakthroughs in making them smarter. There are a lot of tasks that are really tough for classical computers to handle, like classifying web content with high accuracy, really understanding the relevance of something to a specific topic, extracting the most important information automatically, or even, spotting malicious or misleading content. And QML algorithms could be a game changer for all of those things.
That's fascinating. So not just faster and more efficient, but actually more intelligent.
Right.
And then the research actually proposes a specific architecture for this kind of quantum-enhanced web crawler. It's a layered architecture. So can you walk me through how these different quantum and classical pieces would actually work together?
Yeah, so the proposed architecture has multiple layers. You'd still have that classical web crawler layer doing the basic stuff, like managing the URL frontier and fetching pages. But then you'd add a quantum processing layer, where all those powerful quantum algorithms, like Grover's and QML, would do their thing.
Right.
And then crucially, there's a quantum communication layer. And this is where quantum teleportation comes in.
Yeah.
Because it allows for really fast and efficient transfer of quantum states between different nodes in the crawling infrastructure.
So quantum teleportation is like the super fast highway connecting everything together.
Exactly.
Okay, that makes sense. So we've got all these different parts working together, but what about actually integrating them, And what about all that data? How would we manage and store all of that?
Yeah, that's a huge question.
Mm.
The proposed architecture includes an integration layer to manage the interaction between the classical and quantum parts, and then a storage layer.
Hmm.
And that storage layer would probably be a mix of, our traditional technologies and some newer, potentially quantum technologies. So, traditional databases like relational databases like PostgreSQL, NoSQL databases like MongoDB,
Yeah.
and distributed file systems like Hadoop, HDFS. They'd probably still be used to store most of the crawled data.
Okay.
But the research also talks about some really interesting next-generation technologies, some of them quantum, some inspired by quantum principles.
Yeah. Can you give me some examples? What kinds of things are we talking about?
Well, there's this idea of quantum CDs,
Hmm.
and they're trying to use different properties of light to store way more data on optical media.
Wow.
And then there's research into advanced materials, like gold-plated superconductors, which could make quantum data storage much more reliable and long-lasting. And then, in the world of quantum-inspired tech, you've got things like Amazon QLDB, which provides a cryptographically verifiable ledger,
Hmm.
and there's also a lot of work being done on super-fast, high-fidelity quantum memory systems.
Okay, so it sounds like the future of data storage for web crawling could be this really cool mix of tried and true classical systems and these potentially revolutionary quantum era methods. So, how does the research suggest we actually go about building this quantum enhanced crawler? What's the plan?
Well, they lay out a roadmap with different phases. So in the near term, the focus is on strengthening our classical infrastructure,
Mm.
making sure we have really robust and scalable distributed crawling systems and efficient databases in place.
Right, solid foundations.
Exactly. And then there's a big emphasis on integrating those quantum-inspired components like those advanced ledger databases we were talking about.
Okay.
And of course, a lot of effort will go into researching and developing quantum algorithms that are specifically designed to tackle those web crawling challenges.
Makes sense. And what about the medium term? What are the next steps there?
When in the medium term, as quantum hardware gets better and more widely available, the roadmap says we'll start actually implementing those key quantum algorithms, like using Grovers for smarter URL selection and using quantum algorithms to find near duplicate content.
Right.
And this phase will also involve a lot of work on integrating those quantum components with the existing classical systems.
Yeah.
And we'll probably start seeing some early targeted deployments, for specific high-value crawling tasks,
Hmm.
just to see how they perform in real-world situations.
And the long-term vision, what does the research say about what web crawling might look like 5, 10 years down the road?
Well, the long-term vision is pretty ambitious. It's all about deep integration of quantum tech.
Okay.
So we're talking about the possibility of having lots of quantum processors within the crawling infrastructure, a fully functional quantum teleportation network for super fast communication,
Yeah.
and maybe even using quantum storage technologies for certain types of data.
That's a big shift.
Yeah. And the focus then would be on developing even more sophisticated quantum algorithms
Hmm.
for things like advanced topic modeling and natural language processing, really understanding all that web content,
Hmm.
and then analyzing the web structure as a massive network, like a giant graph,
Hmm.
and detecting anomalies and patterns in the data, and building super personalized recommendation systems to guide the crawlers.
Wow.
Yeah, they even talk about developing a whole ecosystem of quantum-enhanced web technologies. It's a really exciting vision.
It definitely sounds transformative, but the research is also pretty honest about the challenges ahead.
Oh, yeah. And there are some really big ones.
What are some of the biggest hurdles we have to be realistic about?
Well, the biggest one is probably the current state of quantum hardware.
Hmm.
The quantum computers we have right now, they have a pretty limited number of qubits.
Okay.
And those qubits are still very sensitive to decoherence. They lose their quantum properties pretty quickly.
We talked about that.
And the error rates in quantum operations are still high. And the way qubits are connected within a processor isn't always ideal.
So the hardware itself still needs work?
Definitely. And then there's the whole challenge of actually integrating these new quantum systems with our existing classical infrastructure. That's a huge engineering task.
I can imagine.
Yeah, creating reliable interfaces between those two types of systems, dealing with the communication overhead, figuring out how to program them effectively, how to allocate tasks to the right type of resource, And then debugging quantum systems. That's way more complicated than with classical systems. So yeah, there are a lot of technical hurdles to overcome.
And beyond the technical stuff, there are also just, practical considerations.
Right.
Like quantum computing resources are really expensive and not easy to come by. And we need more people with the right expertise. And the whole support infrastructure for quantum tech is still being developed. And there are no real industry standards yet.
Yeah, and potentially even regulatory hurdles. So all of that really underscores that even though the potential is huge, we're still very early in the process of actually using quantum computing for something as complex as web crawling.
So, big challenges, but also huge possibilities. So, looking ahead, what are some of the areas where future research could really make a difference?
Well, the research points to a few key directions. One is developing better quantum algorithms that are specifically designed for web analysis.
Okay, so like tailored algorithms for specific tasks.
Exactly. Things like better algorithms for topic modeling,
Mhm.
natural language processing, analyzing the web structure, finding anomalies, and building smarter recommendation systems.
And it also mentions quantum enhanced search engines.
Right.
And that's not just about crawling, it's about, changing how we search for information altogether.
Absolutely. Future research could look at how quantum technologies could revolutionize every part of the search process,
Okay.
like building those massive search indexes, understanding user queries better, ranking search results more accurately, personalizing searches, and even developing completely new ways for people to interact with information online. Really exciting stuff.
And then there's this whole other area about the future of the internet itself, right?
Yes, the quantum internet.
And how that intersects with web crawling. It's almost like we're talking about science fiction here.
It really is.
Yeah.
But as quantum internet technologies get better, we could see all sorts of new things happening,
Mhm.
like new quantum web protocols for secure communication, new ways to distribute web content using quantum channels, much stronger web security with quantum cryptography, new quantum web standards, and maybe even new types of decentralized web applications that use the power of quantum networks. It's mind-blowing to think about.
Yeah, it really is. So as we wrap up this deep dive, it's pretty clear that combining quantum teleportation and other quantum computing tech with web crawling has incredible potential.
Hmm.
We've still got a lot of work to do, both on the engineering side and the scientific side.
Right.
But the possibility of making web crawling so much more efficient, faster, and resource savvy, it's really transformative. And it seems like the future is going to be a hybrid one, right? Where classical and quantum computing work together.
Yeah, definitely. A synergy of those two worlds.
And as we've discussed, the impact goes way beyond just crawling itself. It could change how we search, how we keep things secure, and how we interact with the web as a whole.
It's a really exciting time to be thinking about these things.
It really is. It makes you think, The idea that how we access and understand information online, that something so fundamental could be completely reshaped by quantum mechanics. That's a really profound thought. Well, thanks for joining me for this deep dive. I hope you found it as mind-expanding as I did.
Thanks for having me. It was a great discussion.